Hello, welcome to another lecture. This one is going to be a bit intense because we'll be doing some mathematics. So you might want to grab a piece of paper and a pen, and please pause the video as many times as you want. I mean, that's the nice thing about video lectures. You won't fall behind, right? If you don't understand something, slow it down, try to work it out yourself, and hopefully you'll be alright. In the previous lecture, we spent some time talking about recurrence equations of define conquer algorithms, but we never actually used it to derive the complexity of the algorithm. Well, we did it in a hand-wavy way, saying this is the number of levels, this is how many operations you have to do on every level, thus this is the algorithm. But it's not a formal way of doing it. So that's what we're going to be doing today. In a way, this is not so bad because you kind of done this in COM2D5, COM 2010. And like I said, we're just going to do it more formally. So here are the steps that you have to do. And you should kind of know this, right? The first thing that you do, you draw out the recursion tree. Just until you can see some sort of pattern, like how you divide it. One or two level, or 2 or 3 levels should be enough. But the focus of the recursion tree is on the costs of each node. Like for each node, you're gonna be writing down the number of the size of data that you have left for that subproblem. This will be obvious. And then you count the number of operations on each level. You count the number of levels, and then you can work out the total number of operations. Simple. So we're probably going to get started with Mergesort again. So with the recurrent tree or search space or search tree, whatever you want to call this. The focus used to be on how we break down the problem into subproblems. So here, if you have to do Mergesort on the whole array, you'll be breaking down the array into 2 parts, from 0 to n-2 and from n-2 to n. Now, as I said, the focus is going to be how big is the input on every sub-problem. So we'll be looking at it like this now. Okay. We see that we have n elements at the top. And then on the second level, we have n over 2 elements. And then on the next level, we have a quarter of that, n over 4, on each recursive call. And here is the what should I call it? Recurrence equation? Yeah, this is the recurrence equation for Mergesort. Right, for every tn, we have to do 2 recursive calls of size n over 2 each. And on every level, we have to do cn operation, where c is just some constant. And there are some assumptions that we're doing to make the analysis simpler. We're gonna say that n is just a power of 2. Well, because we divide it by 2. It'd be nicer if n is a power of 2. And we are doing cn operation on each subproblem size n, so where c is just some constant, and we are doing 1 operation on the leaves of the tree. That's the assumption here. So we talked about this in the last lecture, and where we can afford to be a bit sloppy because it doesn't make that much of a difference, especially on the non-exact division and on the boundary conditions. So let's get started. Okay, step 1, draw the recursion tree. Here it is. So Tn, again, is the number of operations that you're doing. That depends on 2 times Tn over 2. So you have these 2 here. That depends on 2 times Tn over 4, and so on. That's your recursive function. And on the leaves, you have 1 operation each. That's the recursion tree. But of course, now the focus is on the number of operations you're doing, which depends on the size of the data that you have, like the size of the input. So on the top level, you have to do cn operations. On the second level, you have to do cn over 2 operation twice, and then cn over 4 operation 4 times. So if you just sum up the number of operations on every level, that's just cn, cn, cn. And at the bottom here, well, you will be doing n operation, actually. But I'm just going to write theta n here, because you're not exactly doing n operation, right? You'll be doing cn operation as well. So I can write theta n. This is also how the textbook does it. And I think it's actually a good way of doing it because, again, it's not exactly n operations. It's a constant time n. So it's the same thing if you just write theta n. But later on, you'll see that if you want to, you can just write cn there as well. Now, we have to work out the height of the tree. We have to count the number of levels. So how do we do that? Well, let's see how much work we have to do before we get to the bottom of the tree. On every level, we divide the problem by 2. Right? We start with n, then we go to n over 2, n over 4, all the way up to n divided by 2 power of I. Because again, n is some power of I, so we're just going to pick a nice n that will divide nicely. The final level is when n divided by 2 to the I is equal to 1. In other words, 2 to the I is equal to n, or I just log base 2 of n. So there are log base 2n levels. So just to check, level I, the last one, how many nodes you have? You have 2 to the I nodes. So, sorry, on every level you have 2 to the I nodes, which means that final level you have 2 to the power of log 2n nodes. And we discussed this identity in the workshop. 2 to the power of log 2n is just n nodes, as we expected. Okay. So we got the number of levels. We got the number of operations on every level. And now we just need to find the number of, the total number of operations. And we did this in the last lecture anyway. It's just n times log base 2 of n. So Tn is just big theta n log n. See, this is fine, but we're hiding a bit of complexity here because the problem is so easy. What am I talking about? All right, if you go back to the recurrence tree, you see that on the final level here, we're doing theta n operations. So on every level, we're doing cn operations. But on the last one, we say we're doing theta n. And that's not exactly cn, is it? Because you have 1, 1, 1, 1, 1, 1, 1 here. It's actually n, not cn. Well, you have n nodes at the bottom. We know that. So you can't just write cn at the bottom here. This is why I have theta n, not cn. Okay? So why does that matter? Well, actually, this is what we have. We have cn plus dot 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 plus cn, not log n times, but log n minus 1 times. All right, so that's the that's the number level except for the last one. And then on the very final level, you add theta n. Of course, this is still theta n log n. This is fine. I mean, like I said, this problem is so simple, such that we don't really have to think about this part here. But in the later examples, you're going to see why this kind of matters a bit. I guess at the end of the day, it doesn't really matter that much because if you have Cn, then that is still theta n. But if you are mathematically inclined, you might not be so happy about having all 1, 1, 1, 1, 1 and then adding up to Cn because, well, obviously that's not true. Okay, so just keep that in mind. And now we're going to go to the second example. So the second example that we have is something that we've done in the previous lecture as well. We're going to be talking about linear search. But I'm going to write the linear search like a binary search-ish. As in, I'll look at the middle element. And if that's the target, I just go back. Otherwise, I recurse to the left and to the right. About half each. Hope you remember. And so the recursive equation is 2 times the n over 2 plus theta 1. That 1 there is the comparison operation that we're doing here. All right. Well, I guess the division and the comparison operation. So if you want to, you can say you're doing 2 operations, which is still theta 1. Okay, step 1. Draw the recursion tree. Here it is. Again, we assume that n is the power of 2, so we have a nice evenly balanced tree here, and we are doing one operation on every node. Just say we're doing one operation, not two. What else? I guess we should say that the focus is on the size of the data again, so I'm going to write it like so. And do you think this is correct or is this wrong? Like, have a think. So we're doing one operation on every node. So why do I have Cn and Cn, Cn, Cn here? Well, because it's actually wrong. This is the Mergesort one, and on the Mergesort, on every level you're doing n operations, well, Cn operations, because on every node you are doing n operations. This is linear search now, so we're not going to be having Cn, Cn over 2 anymore. We can actually say that on every node we're just doing one operation. Okay, just like I said that we will. So that's the number of operations on each level: 1, 2, 4, 8, and so on. So how many operations are we doing on the last level? Okay, so the final level, as before, as the case of Mergesort, is when n divided by 2di is equal to 1. Alright, so you have n elements, and we say that n is perfectly divisible by 2, n is the power of 2. And when you get to the ith level, that last level I is when I is equal to log base 2 of n, just like Mergesort before. Okay, and we know that on the level we have n nodes. So the total number of operations I have to do on the last level is big theta to the power of log 2n, which is just theta n. So this is just like Mergesort again. But this time around, you don't have Cn on every level, you just have theta n on the last one. All the ones before should be less than n. Sorry. So do we know the number of levels? Yeah, well, it's still log base 2 of n levels. And now we just need to count the total number of operations. Now, unlike Mergesort, you can just multiply log n with the number of operations on each level, because the number of operations on each level changes, it actually increases as you go down. So you need to find the sum of 1 plus 2 plus 4 plus dot 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 plus n, right? And we still need to add this theta n here. Sorry, I'm missing the theta n from there. Let me fix that. Okay, fix. So we have to find the sum of 1 plus 2 plus dot dot dot, like powers of 2, up to 2 to the power of log n minus 1. And then the last level gives you, well, the last level is just theta n. So we'll keep it like that. We'll keep it like that. So we have the summation here. Okay. So how do you get that? Well, you have to use the formula for the geometric series. And you can find this in CRS Appendix 2, Appendix A. So here's the formula. And I'm going to give you this formula in the exam if you need it. So you don't need to memorize the formula. Or if it's an open book exam, you can find it online anyway. So let's just work out how to use it. All right, so we have to find the sum here. The formula is x to the n plus 1 minus 1 divided by x minus 1, where m is the final index there. So we're going to sum into the decay from 0 up to log n minus 1. So just sub it in, you will have n minus 1 as the sum. The total number of operation is therefore n minus 1. That's on the from all the level except for the last one, plus theta n, which is the last level. And of course, that is still theta n. So linear search is theta n. All right, so 2 examples so far. Hopefully that's still easy. Now, the nice thing about doing this kind of recursion tree is that I can change the linear search into You remember how I divided linear search into 3 sections? So instead of just dividing the array into 2 sections, I divide the array into 3 parts. I get the largest element from each part of the array, and then I have to compare 3 numbers, right? So we're doing one operation on each node. We're doing that comparison. And this is the recursive equation. 3tn/3 plus theta 1. I should probably say that we're doing theta 1 operation, not one operation, sorry. Let me fix that as well. This is going to matter in a bit. You'll see why. Alright, so I'm going to skip some steps here. You can follow the same steps that we did for the previous case, and you'll end up with this tree where you have to do 1 operation on the first level, and then 3, and then 9, just powers of 3 basically. And remember that n is a power of 3, so you will have a nice integer here, like a nice whole number. And again, at the bottom, you have to do theta n operations. So this time, you have to work out the sum of powers of 3 up to 3 to the log base 3 n minus 1. Again, because there are log 3 n levels. So and the last one is theta n, remember. So we have to find the sum up to log base 3 of n minus 1. Alright, so again, apply the formula for geometric series. We have the sum to be n minus 1 over 2. So again, linear search is theta n. But do you see something dodgy here? So this is a mistake, and it's intentional this time around. If you're looking for an element inside an array and it's not sorted, if you do linear search, then you have to look at every single element. So how can you say that the complexity of the algorithm is n minus 1 divided by 2? Like, you're only looking at half the elements in that, if that's the case. I'm guessing the most expensive operation is the comparison operation, right? Because what happened is on every node, we're actually doing more than just 1 operation. We're actually doing 2 operations. So if you remember how I did it, the code with this with the binary search, well, I can't call it binary search. What do I call it? Binary linear search. The linear search where I divide the array into 2 parts. What I did was I look at the middle element and I see if that is the element that I'm looking for. So that's the 1 operation, the 1 comparison. But now if I divide the array into 3 parts, that means I'll be looking at the element 1/3 of the way and then 2/3 of the way. And I'll be comparing those 2 to the element I'm looking for. So I'm doing twice the number of operations that I'll be doing if I just divide the array into 2 parts. Okay, so hopefully that makes sense. So there is a 2 here, like on every node, not just 1. And the good news is it doesn't really change the equation much. You just put 2 in front of every single one of them. So you put 2 outside here. But now you will have, you will nicely have n minus 1 as the number of operations that you're doing in this linear search version. Which makes sense. Like, linear search, doesn't matter how you do it, you should still do n minus 1 operations. Yes, that is an example of what can go wrong if you miscount the number of operations you have to do on every node. Again, in the general scheme of things, it doesn't really matter that much because in both cases, you can just say this is still theta n. Right? Even if you had like n minus 1 over 2 here, that is still theta n. But yeah, in some cases, you want to be careful with the formula. You want to be careful in how in what you're counting to make sure you don't undercount or overcount. It doesn't matter in this one here, but it may make a difference in other ones. So we have 2 examples now, or 2.5 examples, I guess. And I hope you're still following alright, because this is really something that you've done before. You just draw the tree, you work out how many operations you have to do on every level, and then you work out the number of levels you have. Except that this time, remember that the last level, you should put theta n as the number of operations on that level. And also this time around, it's a bit harder because the number of operations you have to do on every level may not be the same. As you can see, it actually increases, like 1, 2, 4, 8, or 1, 3, 9, 27, so on. Which is why we have to use the formula for geometric sum in some of them. But apart from that, it's just something that you've done before. So shouldn't be no dramas. Now let's do the textbook example. This is from CLRS, page 89 to 90. And this is going to be a bit more intense than what we've done so far. I think the two examples we've done are quite simple. This one's going up a notch because we're going to do 3 times the n over 4 plus cn squared. I'm not sure if you have seen this kind of algorithm before. I can't think of anything on the top of my head. But basically, this is what the recursion tree looks like, right? If you have n elements at the start, then every time you recur, you use 1/4 of the element. And we're going to assume that n is power over 4, so it will divide nicely all the time. Now, the number of operations you have to do on every level is going to be cn squared, where n is the size of the data at the time. So if you have n over 4, then you will have to do c times n squared over 16. And then on the next level, it's going to be cn squared over 256, and so on. And we're just going to say that at the very bottom, you're going to be doing one operation on every node. So again, let's draw the tree. Let's count the number of operations on each level. We have cn squared, followed by 3 over 16 times cn squared, followed by 9 over 256 times cn squared. And what about the final level? All right. Let's work out the height. This time we define the problem by 4 every time. All right, so we go from n to n over 4 to n over 16, all the way to n over 4 to the I. And because, again, n is an exact power of 4, we're going to stop when I is equal to log base 4 of n. Now, at the very bottom, you have 3 to the power of I nodes. So at the very bottom, you have 3 to the power of log base 4 of n nodes. So this is what the tree looks like. This is the number of operations we have to do on every level. And now let's work out the formula. Okay, so this again, we have all the levels here except for the last one, and the last one I'll write as theta, 3 to the log 4 n. So this is a sum that we have to work out. And we can see I can pull out 3 over 16 on each one of them. This is just, every term is just a power of 3 over 16. Okay? So I have to work out the summation. Let's grab the summation formula again, the formula for geometric progression. I get that. And this is ugly, this is hard. I really don't want to work out this fraction here. So what I'm going to do is I'm going to cheat a little bit more. I'm going to use the formula for an infinite series. So the one that you saw before is a formula for series going from 1 plus x squared plus x to the m. If you allow the index, the exponent to go to infinite, then the formula becomes 1 divided by 1 over x, 1 divided by 1 minus x, if x is less than 1. Okay? If x is greater than 1, then the sum will not converge. But if x is actually less than 1, it can converge to this number here. That's the limit. So that's what we're going to use. How are we going to use it? Well, if I have the partial sum up to n, then we know this is less than the sum to infinity, right? Because so you have the sum to infinity here. You're just going to stop at n, whereas this one goes to infinity. So obviously, this one is going to be much higher, much bigger. And we know that the limit of this sum is 1 over 1 minus x. So here's the sum that we have to do. That's going to be smaller than the infinite sum here. All right, I'll keep the theta over there. The theta doesn't change. And instead of like the ugly, what did we have before? Instead of this ugly 3 over 16 we have 1 divided by 1 minus 3 over 16, which is just a nice constant. It's just a little bit above 1. Now we're going to use one more rule. I don't want to prove this in the lecture. You can find the proof online, or we can chat about it during the workshop if you need to know the proof. Basically, if you have 3 to the power of log base 4 of n, well, doesn't matter what the base is, you can just swap the 3 and n around, right? So you have this. Why do we care about this? Because while we have the summation nicely here in n squared, you got something here. You got something inside the theta, which is 3 to the power of something. And you got to make sure that, well, you got to make sure that's not exponential, right? You have to know what that is, right? You got to be able to convince yourself that that is polynomial, and actually it is, because if I just use that formula here, I'll solve the 3 in the end. I get n to the power of log base 4 of 3. Now, log base 4 of 3 is about 0.79. So this is big theta and 0.79. Which is less than n squared. So good news, the complexity of this algorithm is just big of n squared. Now, just a little aside. So on all the examples we have so far, I always say that the last level should be treated differently. I always write big theta something. So in the last case there, I'll say the last line we're going to have big theta 3 to the log 4n operations. But when you think about it, this last term here is just 3 over 16 to the power of log base 4 of n. Like it's just the next term where you increase the exponent. If you want to measure y, then let's just write that. So I can expand the brackets here. So I have 3 to the power of log n, and I have 16 to the power of log n at the bottom. And it goes 16 to the power of log base 4 of n, which is 4 squared to the power of log base 4 of n. And I just switch around the powers. I just get n squared, right? Because 4 to the power of log base 4 of n is just n. So you got n squared there. Meaning that, well, now I can divide n squared away. So I end up with some constants times 3 to the power of log base 4 of n, which is just theta 3 to the log base 4 of n. Okay, so this is just the next term. Well, I mean, this theta here is really just the next term. If you have some constant for it. So if you really want to, you can just find the summation for the whole thing. I would prefer if you still write the last level as theta something, because again, it's a lot more, well, I guess it's more terse, because we say that every node we're just doing one operation. But even here I wrote theta 1, not 1. So really, I'm not too fussed. But again, that's all there is about Recursion-Tree Method. Hopefully that wasn't so bad. Again, something that's new here maybe just the use of the geometric sum, and maybe you think the mathematics is yucky. We're gonna do more in the workshop, and I'm gonna make one of the submission question about recursion tree. Oh, also about the next method, the substitution method. And this is going to show up in the exam or the class test. But like I said, I'll give you the formula. So, but you have to be able to show me the steps. You have to be able to show here's the tree, here's the number of operation on every node, here's the number of operation on every level, how many levels there are. Hence, this is the total number of operations. Okay. And from my experience, this wasn't done so well in previous exams. Like, even when I told the students, hey, this is going to be an exam, it shows up. Because I guess a lot of students see math, they see formulas, they see Greek symbols, and they go, I don't want to do this. But really, I don't think this is hard. Just play around with the formula, just putting in stuff inside the formula, and then do some algebra. It's not hard algebra, so do your best, have some practice, and then try to ace the exam if this comes out. All right? Okay, I'll see you in the next lecture.